Hello, welcome back. This is Physics 102A, the homework solutions for Chapter 6 on momentum and collisions, and also included is center of mass. We start with number 29. Three masses are at different points along a 2-meter stick, and it gives the masses at each position. Where is the center of mass? And this is a multiple choice question in the book. We're going to use the formula that the position of center of mass of a group of objects is the sum of every mass times its position on the coordinate system divided by the sum of the masses. And the positions are given in the problem. So here we have the 0.45 kilogram, and it says it's at 0.8 meters. We have the 0.6 kilogram at 1.1 meters, etc. We divide by the sum of the masses, and we get 1.3 meters. Which in the multiple choices is answer C. Number 31, a 0.2 kilogram ball and a 0.4 kilogram ball approach from opposite directions. Initially, the 0.2 kilogram is moving at 3 meters per second to the right, and the 0.4 kilogram is moving 2 meters per second to the left. After a collision, the 0.2 kilogram ball is moving 3 meters per second to the left, and the 0.4 kilogram ball is doing what? And in the book, it's multiple choice. All right, so this is a conservation of momentum problem with collisions. And we need to make sure that we are assessing the direction left and right. So I'm calling to the right the positive direction and to the left the negative direction. Here's a picture that I've drawn with M1 moving at V1, 3 meters per second, M2, and notice what I've done here. I have to make V2 negative 2 meters per second because it's to the left. After the collision, the problem says that ball 1 is moving at a velocity of 3 meters per second to the left. So notice my notation. I'm calling it V1 prime. The prime means after the collision. And I've put in the negative sign. It's moving negative 3 meters per second. And we want to know what is V2 prime. So we'll set up conservation of momentum. So the momentum of ball 1 plus the momentum of ball 2 before the collision equals the momentum of ball 1 plus the momentum of ball 2 after the collision. I'll turn all the p's for momentum into m times v, so m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime, and we solve for whatever we need to solve for. And here it's asking for what is v2 prime, so we'll go through the algebra. And v2 prime, when we plug in the values, we get positive 1 meter per second. Now the positive means it's moving to the right. And so that's answer B in the book, 1 meter per second to the right. Number 33, what minimum force is needed to accelerate a bicycle and rider with a combined mass of 105 kilograms to 15 meters per second in 8 seconds? What is the system's momentum at that time? So this involves the relationship between force and momentum. It's actually the more generalized version of Newton's second law, that the average force is the change in momentum over the time. And since masses are given and velocities are given, let's turn that delta P into m delta V. Now, there's an intermediate step. We could call it delta mv. But when you have something that's changing, anything that's constant, in this case mass, can go out to the side of the delta. So it becomes m delta v over delta t. And so we have the mass of 105 kilograms times the change in velocity. It says to go to 15 meters per second, and the inferred in there is that it's coming from rest. And so times 15 meters per second is the change, doing it in 8 seconds. And so we get 197 newtons. The question then asks, what is the system's momentum at that time? Momentum is mass times velocity, so 105 kilograms times 15 meters per second, and we get 1575 kilograms meters per second. Number 37, a 145-gram baseball moves horizontally toward the batter at 34.5 meters per second. If the ball leaves the bat at 39.2 meters per second in the opposite direction, find the impulse imparted to the ball. We have to be careful that there are two separate directions here, so we're going to have to notate left and right, or initial and final direction, as negative and positive. And so you can look at the picture that I've done. It leaves the bat 39.2 meters per second in the opposite direction. So the way I've drawn it, I've made initial velocity be negative. So going to the left, final velocity going to the right. The impulse is the change in momentum. So change in momentum is mv1 minus mv0. And when I can factor out the m, so it's m times v1 minus v0. The v1 is positive 39.2. The v0 that we're subtracting is negative 34.5. And so when we calculate that, we get an impulse of 10.69 kilograms meters per second. Number 43. A net force of 0.340 newtons I hat plus 0.240 newtons J hat is applied to a 170-gram hockey puck for 4.5 seconds. If the puck was initially at rest, find its final momentum. And if the puck was initially moving with the given velocity, 2.9 meters per second I hat plus 1.35 meters per second J hat, find its final momentum. All right, let's list out the given information. Here's the force in vector form, the mass, the time increment. We want to find its change in momentum. So its change in momentum, otherwise known as the impulse, is force times the time. Now, change in momentum is final momentum minus initial momentum. I call that P minus P naught. So let's solve for P. P, the final momentum, is P naught plus force times delta T. And we're going to use this equation for both parts A and B, so I'm just leaving P naught written as it is. But then the force times delta T, you can, the force is given up above times 4.5 seconds, and there it is. And now we'll address parts A and B. Part A said the puck was initially at rest, so P naught is just 0, 0. So when we add the vectors, it ends up to be the same as F delta T, so 1.53 and 1.08 kilograms meters per second. For part B, it gives an initial momentum. It gives an initial velocity, and we can easily turn that into momentum. So velocity is 2.9 I hat plus 1.35 J hat. Let's multiply both of those by the mass to get our I hat, J hat for momentum, then add the F delta T, and you should get 2.02 I hat plus 1.31 J hat kilograms meters per second. Number 55, conservation of momentum. A 130-gram meteoroid is at rest at the origin when internal pressure causes it to burst into. One piece with mass 55 kilogram moves off at 0.65 meters per second in the positive x direction. Find the velocity of the other piece. All right. Let's draw a picture here. We have the first one. We'll give it a mass of, 55 grams. Actually, that's the second one. Mass of 55 grams, and it moves off at 0.65 meters per second. So I've called it V2 is plus 65 meters per second. The one that's going to clearly move off in the negative x direction is the remaining part of the rock, and its mass is, well, it started as 130 grams. 50 grams went in one direction, so the rest of it, 75 grams, goes in the other direction. And we want to know what its velocity is going to be. We'll say V1 equals question mark. We're going to use the momentum, the total momentum before the action is the total momentum afterward. So before the action, the rock is at rest, so there was 0 momentum. equals, after the action, m1v1 plus m2v2. And we want to solve for v1, which is the velocity of the one that I've designated m1. Go through the algebra and we get negative m2v2 over m1. Plug in those values. As long as we are consistent with the mass units, we don't need them to be in kilograms. They're just the same. They're grams and grams. Those gram units are going to divide out. And what we're left with is V1 is negative 0.477 meters per second. And that means that it's 0.477 meters per second in the negative x direction. Number 59, another conservation of momentum problem, particularly collision. We have a car going at a given speed. It hits and sticks to the bumper of a stationary car with a given mass. Find the speed of the joined cars immediately after the collision. So this is what's called a totally inelastic collision, where the two stick to each other. We'll use conservation of momentum. So we can say the momentum beforehand is m1v1 plus m2v2. Now, car 2 was at rest. v2 was 0, so that part just goes to 0. I've just crossed through it. Equals, after the collision, they're stuck together, so we can just consider them to be one big car. m1 plus m2 is its mass times the velocity v prime. We solve for v prime algebraically. We get m1 v1 over m1 plus m2, and we get 1.61 meters per second. Notice that it's a little less than half of what the original car was going. If they had been equal masses, it would be half of what the original car was going, 1.7 meters per second. But the original moving car is a little less massive, so it doesn't quite retain half of its speed. It goes down a little bit. Number 76. In beta decay, so this is nuclear physics here, a neutron at rest decays into a proton and electron ejected in opposite directions. And we will, as the book says, cover beta decay more next semester in chapter 25. If the electron speed is 7.25 megameters per second, what is the proton speed? So here we have, before the decay, it's a neutron just sitting at rest. It's got no momentum. Afterward, we have a proton going in one direction, the electron going in the other direction. So I have the velocity of the electron as plus. I'm making it plus because I'm making it go to the right, the positive direction. 7.25 megameters per second. Velocity of the proton is what we want to find out. You can look up in the front flap of the book what the mass of a proton and electron are, but there they are to 4 significant figures. Let's do conservation of momentum. So the momentum of the neutron, which is 0, is equal to, after the action, the momentum of the proton plus momentum of the electron. That becomes mpvp plus meve. We're going to solve for velocity of the proton. We get negative mass of the electron times velocity of the electron over mass of the proton. And now when I plugged in these numbers, I kept the speed in megameters per second. So the answer I get was velocity of the proton is negative 0.003947 megameters per second. And the negative means going to the left, which we already knew was going to happen. And so we can turn this, let's do it in scientific notation in meters per second. So I can convert this to meters per second, and it's 3.95 times 10 to the third meters per second. And the negative just means it's going to the left. Number 89, two masses are placed at different points along a meter stick of negligible mass. 0.25 kilograms at 0.2 meters and 0.5 kilograms at 0.5 meters. And you can see my picture down below. Where's the center of mass of this system? Now, notice that it says a meter stick of negligible mass. So we're not going to be concerned with the stick of negligible mass. The meter stick is just there as a rigid body to hold the things in place, but we're not going to be concerned about its mass. So we're going to use the center of mass equation, which is the sum of every mass times its position, divided by the sum of the masses. So the 0.25 kilograms times 0.2 meters, this one to the left, plus the 0.5 kilograms times 0.5 meters, the one to the right, divided by the sum of their masses, and we get 0.4 meters. And so here we have the balance point. Number 93, on a seesaw, a 28 kilogram child sits 2.8 meters from the pivot point. Where should a 38 kilogram child sit to put the center of mass at the pivot? All right. So we're going to use our center of mass equation. I've drawn a picture here. We want the center of mass to be at the pivot, which is right in the center of the seesaw. And so we're looking for our center of mass equation, and we're looking for it to equal 0. And we are looking to solve for x2. So let's write out the equation. X center of mass equals, and there it is for 2 masses. And for this problem, 0 is the center of mass, so let's substitute 0 for that. Now, when you have 0 equals a fraction, you have a numerator over the denominator. It doesn't matter what the denominator is. All that matters is the numerator, and that numerator has to be equal to 0. So in the next step, one way to look at what I've just done is I've eliminated the denominator. Because again, if a fraction equals 0, the numerator equals 0. So don't even care what the denominator is. Another way, more mathematically, you can think about it is that I've just multiplied both sides of the equation by that denominator. So I've multiplied both sides of the equation by m1 plus m2. That gives you 0 on the other side and leaving you with the numerator. And now we can solve for x2. Notice the distance the child is going to sit is the ratio of their masses times the position of the first child. And there is that negative sign in there. When we plug in the values, 28 kilograms over 38 kilograms, negative, and the position of the first child is negative 2.8 meters, so 2.8 meters to the left. And mathematically, that will make the position of the other child have a positive position. And that comes out to be 2.063 meters. So we can say, using proper significant figures, we only get 2 significant figures here, so we should say 2.1 meters from the pivot. Number 94, you have a 120-gram meter stick. So for this one, we cannot neglect the mass of the meter stick. Where should you place the meter stick atop your finger so it balances? Okay, that's an easy one. If it's a uniformly distributed mass, as meter sticks tend to be, then the balance point is right in the middle. So the center of mass is going to be at the center of that meter, so at the 50 centimeter mark. Now, question B. Where is the balance point if you place an additional 100-gram mass at the 20 centimeter mark and a 200-gram mass at the 80 centimeter mark? So you look at my picture, we have the mass of that little subscript there in the middle is R, the mass of the ruler. And for purposes of the center of mass equation, we're going to say that the mass of the ruler is concentrated at its center of mass, so at the 50 centimeter mark. There's also M1 and M2. Now I've given all the information here. Mass of the ruler, 120 grams. And even though the ruler is spread out over the full 100 centimeters, we can, for mathematical convenience, we can just say that it's all concentrated at its middle, at its 50 centimeter mark. M1, 100 grams at 20 centimeters, M2, 200 grams at 80 centimeters. And now we plug those values, the masses and the positions, into the equation. Notice the units I've kept are grams and centimeters. That's okay. Grams are going to divide out. We're going to be left with centimeters, and we get 57.1 centimeters. So you can see my picture towards the bottom, where the red triangle represents the balance point. And it's going to be a bit to the right, we expect, of the middle mark because the small mass, the 100 grams and the 200 grams, those are evenly spaced. They're both 30 centimeters from the middle. But the M2, the 200 gram mass, it's going to have more mass to it, so it's going to pull that center of mass over a bit to the right. Number 97, here's a problem with two-dimensional center of mass with the origin at one corner of a soccer field. There's a 59 kilogram player standing at coordinates 24.3, 35.9, and a 71.5 kilogram player at 78.8 and 21.5. Where's the center of mass of these two players? Without doing any math, we can just look and we can say, well, it's going to be somewhere between these. It's going to be somewhere on the line between the two of them. And it's going to be closer to the more massive player, the 71.5 kilogram player. So it's going to be, I guess, something about right where my pointer is. All right, so we're going to use the center of mass equation both in the x direction, the y direction. Here I've drawn a picture where the origin is where my pointer is. And x center of mass, only the x positions do we care about. So 59 kilograms times 24.3 plus 71.5 kilograms times 78.8 divided by the sum of their masses, and we get 54.16 meters, which means somewhere maybe about right here-ish, somewhere along this line. This is maybe about 54.16. But now we want to know where along this line. What is the y coordinate? So we'll use y center of mass at the middle of the page, and we'll do each mass times its y coordinate divided by the denominator's the same, and we get 28.01 meters. So we have our x coordinate and our y coordinate. So 54.16 meters to the right and 28.01 meters to the going up, so maybe somewhere around there. The question asked, where is the center of mass? So different places we can express that, and at the bottom of the page I've given that as an ordered pair, which seems the best way to express it because the players' positions were given as an ordered pair. We could also express it as a vector, a position vector, so 54.16 I hat plus 28.01 j hat meters. Number 111, the final problem, is a runaway toboggan of mass 8.6 kilograms is moving horizontally at 23 kilometers per hour. As it passes under a tree, 12 kilograms of snow drops on it. What is its subsequent speed? All right, so here I've drawn a picture. We have the mass M1, it's going at V1, 23 kilometers per hour, and then some action happens. And the action is a lot of snow. In fact, more snow than the original mass of the toboggan is going to drop onto it. Now, I've designated the mass of the snow M2, 12 kilograms. And in my equation, I'm just going to use big M. Big M is the combination of M1 and M2. So 8.6 kilograms plus 12 kilograms. So after the action occurs, after the snow gets dumped, it's a total of 20.6 kilograms. Let's do conservation of momentum. And so we have the momentum of the toboggan, M1 V1, plus the momentum of the snow. Now, the snow did not have any momentum in the x direction. And so, because we treat this as the x and y separately, and we're only concerned about the x direction. But although it was dropping downward, it had no momentum in the x direction. So its velocity, v2, you think its x direction of v2 was 0. And that's going to equal the big mass times v prime, and it's v prime that we want to solve for. So algebraically, we solve v prime is m1 over big M times v1. Notice what the final velocity is related to. It's related to the original velocity times the ratio of the toboggan times the total mass, the toboggan plus snow. Because it is more than doubled in mass, it's going to be reduced by more than half. So we plug those values in, we get 9.6 kilometers per hour. I didn't see a need to convert to meters per second. It gave it to us in kilometers per hour. I kept speed as kilometers per hour, and so there's the answer, 9.6 kilometers per hour. And that is the end of the Chapter 6 homework. Have a great day.